Next up is problem number 2 on the worksheet. It says consider the parabola described by the vector function r of t, which is ti plus at squared j, where a is a positive constant. In part A, it says to use the formula kappa equals the magnitude of v cross a over the magnitude of v cubed to compute the curvature of this parabola. Okay, so we recognize this formula for curvature as what we call the alternative formula for curvature that we derived in the last video. And so to use this formula, we're going to start out by finding our velocity and acceleration vectors. And so for our velocity vector, we want to differentiate the position vector component-wise. So that gives us I plus 2atj. And then for the acceleration vector, we want to differentiate the velocity vector component-wise. And so that gives us 2aj. All right, so next I'll go ahead and take the cross product of the velocity and acceleration vectors. And so when you compute this determinant, you wind up getting 2a times the basis vector k. All right, so now to compute the curvature, I want to take the magnitude of this cross product of v and a. And since a is a positive constant, the magnitude of this vector 2ak is simply 2a. I don't have to worry about an absolute value because, again, a is a positive constant. Now in the denominator, I want the magnitude of v cubed. And I note up here that the magnitude of v, well, that's the square root of the sum of the squares of the components of the velocity vector. So that's the square root of 1 plus 4a squared t squared. So for my expression for curvature, I want to cube that here in the denominator. And so cubing a square root, well, that's just applying this exponent of 3/2 to this expression 1 plus 4a squared t squared. So we get this expression then for the curvature of the parabola. All right, great. So now let's go ahead and look at part B. It says to use the formula kappa equals the absolute value of f double prime of x divided by this expression 1 plus f prime of x squared, all raised to the 3/2 power, to compute the curvature of this parabola. All right, well, we recognize this formula as the formula for curvature when dealing with a curve in the xy plane that's described by the equation y equals f of x. Now here, for this parabola, we are describing it, at least initially, by this vector function, but we recognize the I and the j components as parametric equations for this parabola, whose Cartesian equation is y equals ax squared. So here we're just identifying the parameter t with x. Okay, so let's go ahead and apply our formula, right? If f of x is ax squared, then f prime of x is 2ax, and f double prime is just 2a. And so again, we wind up by just applying this formula with the same expression that we got in part A, right? The curvature is 2a divided by this quantity 1 plus 4a squared x squared raised to the 3/2 power, where again, remember, we're just identifying t and x here for part B. All right, great. So now let's go ahead and look at part C. It says, sketch the graph of the curvature kappa as a function of the parameter t. Where is the curvature a maximum, and what happens to the curvature as t approaches either positive or negative infinity? Well, remember that the curvature is measuring the rate at which our unit tangent vector changes direction as we move along our path. Okay, so first thing to note, by the symmetry of the parabola, right, relative to the y-axis, our curvature function in turn should also be symmetric. And if you graph this function here, you in fact can see that this is an even function of the parameter t. Okay, where is the curvature kappa a maximum? Well, that's going to happen when this denominator is as small as possible, and that's going to happen, since I have a sum of squares here, when t is 0. And see, when t is 0, we are located at the vertex of the parabola, which makes a lot of sense. We're saying, again, right, the rate of change of the direction of our unit tangent vector as we move along our path is equal to the curvature. So it's at the vertex where that unit tangent vector's direction will have to change at a maximum rate. Okay, now what happens as the parameter t approaches either positive or negative infinity? Okay, well, you can see from just this expression for the curvature that the curvature will approach 0 because the denominator is going to blow up in the numerator. It's just a positive constant. Okay, now that also makes sense if you think about moving further along the parabola, either along this right branch or this left branch. Okay, so although the curve is going to continue to increase, the rate at which our unit tangent vector has to turn in order to continue along the path is going to wind up approaching 0. Okay, so that's what we're getting from these portions, these tails of our curvature graph here that you see right down here. All right, great. Well, that is going to do it for this question. Thanks so much.